Okay, good afternoon. My name is Vidinha, and I'm here today to present an approach to predict the fatigue life of composite materials operating in hostile environments. So, in August 2021, Qatar Airways have grounded 20 Airbus A350s due to paint damage. And one of the main concerns publicly cited by the European Aviation Safety Agency was the degradation of the mechanical properties of the composite structure due to moisture exposure. So it is well known that composite materials are subjected to aging when exposed to hostile environments. And in recent years, the adoption of these materials has been increasing in the marine industry due to their excellent mechanical properties. However, using composite materials in hostile environments can significantly modify their mechanical behavior. Extensive research has been conducted to evaluate the effects of hostile environments on composite materials. However, the development of numerical tools capable of correlating the exposure time with the mechanical performance is much less common. Accordingly, the objective of this study is to predict the fatigue life of composite materials immersed in seawater. So in this work, we studied the effects of the marine environment on composite materials, and rectangular samples made of epoxy reinforced with e-glass were immersed in seawater and tested after periods of 230 days and 910 days of immersion. Tensile, static, and fatigue tests were performed, and digital image correlation was used to acquire the strain fields at the specimen surface. So we know that seawater negatively affects the material, and in previous works, we developed a numerical model for predicting the static behavior of these materials after immersion. What I will explain today is how we use the model that we have developed for predicting the fatigue life of these composite materials. So concisely, the developed model is a three-dimensional progressive damage model implemented by combining Hooke's failure criteria and the fixed second diffusion law to simulate the stress-strain response. So here on the graph on the left, we have some measurements of the weight gain and the implementation of Fick's law, and the one on the right, we have the stress-strain curve simulated numerically and obtained experimentally. So the results of the simulations were good, and the immersion in seawater induced a significant reduction in the ultimate tensile strength, as well as a reduction in the ductility of the composite material. And the question is, how can we use the static behavior of a laminate to predict the fatigue life of an immersed sample? So here we have the SN curve of an unaged sample represented in red, and one SN curve of an immersed sample represented in orange. So from an engineering point of view, obviously a control sample has a higher fatigue life NF2 than that of an immersed sample if both experience the same solicitation A. Okay. So how can we acquire the SN curve of an immersed sample from the SN curve of the control sample? Well, the fatigue life of the immersed sample, NF1, can be obtained if we apply the loading conditions B in the control sample's SN curve. But how can we get the loading conditions B? So B can be obtained by knowing the value of delta sigma max, which can be estimated using an energy-based consideration from the stress-strain curves, which I showed previously. So basically, what we do is we calculate the strain energy density between the minimum and maximum stress of the fatigue life in the stress-strain curve. Having the strain energy of the control sample, we then obtain the stress level for which the strain energy of the immersed sample is equal to that of the control sample. So A1 is equal to A2. Then knowing the value of delta A, which is this one, we can obtain the unknown value required for basically knowing the loading conditions B through this equation. So now what we have very concisely was a methodology to calculate the fatigue life of an immersed sample through the control sample SN curve. So what we need is always the SN curve of the control sample and the static response, which can be simulated with a numerical model. So regarding the results, firstly, the experimental results show a significant reduction of the fatigue life. So for instance, at the maximum cyclic stress of 143 megapascal, the fatigue life of samples immersed for 230 days was about 66% of that of the control samples. So this reduction was raised to 95% for samples immersed for 910 days. So what we have in this graph on the left, so the dashed lines represent the predicted results, and the graph on the right, we have those same dashed lines, and we also have some solid lines which represent the mean curves obtained with linear regression from the experimental data. So overall, the numerical predictions were very satisfactory for either for 230 days of immersion or for 910 days of immersion. So in the former case, the ACN curve is slightly conservative, which is positive from an engineering point of view, while the latter one, the numerical results were well balanced throughout the entire range. So in this slide, we have the evolution of the maximum first principal strain around the hole with the number of cyclings. So this was recorded using digital image correlation. These results clearly show a progressive increase of the damage as the loadings are being applied. It also can be seen that damage patterns are similar for all cases, and we can see an asymmetry in the strain fields, although the loading was uniformly applied on the surface. So this asymmetry is caused by two layers of unidirectional laminates, two layers basically oriented with an angle of 45 degrees relative to the direction of the loading. So in this slide, we have these diffractor surfaces analyzed using a scanning electronic microscope. So what we can see in the two images above, they refer to the control sample, while the ones below refer to samples immersed for 910 days. So it is noticeable that diffractor surfaces area of conditioned specimens exhibit a significant fiber matrix separation when compared to the unaged samples. So the unaged samples present a much better bonding between the fibers and the matrix, and accordingly, it can be said that the reduction of the fatigue performance was caused by this phenomenon, and by improving the bonding between the fibers and the matrix, we could enhance the fatigue performance of the glass fiber reinforced polymers in marine environments. So for concluding, so the seawater immersion had in fact a detrimental effect on fatigue performance of the composite tested. So the proposed fatigue life prediction model captured the trends found in the experiments, and it simply requires the ACN curve of the control sample and the tensile tests of the control sample or immersed sample, which can be simulated numerically. Lastly, we can improve by improving the fiber and matrix bounding, we could enhance the fatigue performance of glass fiber reinforced polymers in marine environments. Thank you for your attention. Please feel free to ask if you have any questions.